Continuing on with our conditional probabilities, we have a contingency table here, and we want to be able to find conditional probabilities from this contingency table. As a matter of fact, contingency tables are one of the places where conditional probabilities are very important for real life data and statistical applications. So we have seen this table before. This is the 2011 fall enrollees at the college, at Jackson College, by degree type. Remember, AA is Associate of Arts, Associate of Applied Science, Associate of General Studies, Associate in Science. Certificates, these are concentrations and skill sets. And then there are the males and females. All right, so we're going to select one fall student at random, and we're going to find the following probabilities. And I wrote up in English what this is. So this is the probability of selecting a female student, given that, that's what that vertical bar is, that the student is an AA, Associate in Arts. Letter B is going to be finding the probability that they're an Associate in Arts, given that the student is female. Okay, so the way we're going to do this is we're going to find the probability of AA, or female given AA, by taking the number of female and AA and dividing it by the number of AAs. There we have it. And again, I'm just using the formula up here, right? We're taking the number of both. So in our case, it's female and AAs, and we're dividing it by the given that part, which in our case is AA, right? So we're saying, look, only look at the Associate in Arts students. So only look at this column right here. So if you look at that column right there, what's the chances of being female given that you're in that column? Well, there's 665 female AAs in that column divided by the total of 1194. So this would be 665, oopsie, divided by 1194. And in case you're interested, that is approximately 0.557. Okay, now let's reverse it. So it's the same idea. So it's still going to be female and AA in the numerator. But instead of looking at this column, which is what I did for this one, matter of fact, I will bold this for us. There, yellow. So this one is yellow, right? So we look at that column. We say, okay, given that you're in AA, given that you're in the AA column, there's 665 women in the AA column, so it's 665 over 194. This one's the opposite. Given that you're female, what's the chance of being an Associate in Arts? So that would be looking at this row right here. And not to be all gender normative about it, but I will make it pink. Let's see here. There we go. So given that you're female, what's the chances of being an AA now? Well, it's still the 665, right? That hasn't changed. But it's going to be divided by 4,001 because there are 4,001 female students from that year. So it's going to be 665 over 4,001. So instead of AA on the bottom, Associate in Arts, we're going to do female on the bottom right here. Right? And then this is AA given female, right? Which is 665 over 4,001, which is about 0.166. There, in order to make them match, I had to make them really, really bright pink. So there you go. So 4,001 right there. So that's why 4,001 is my denominator. Now notice these two are not the same problem at all. That order that we put in here in the parentheses, it really matters. Because the first one's saying, hey, out of all the AA majors, what's the chances of being a woman? So let me write that up. 1 second. In other words, if you imagine a room, say like the big theater at the college, filled with all the Associate in Arts majors from that year, that'd be 1,194 people in total. 55.7% of that room would be female. So over half, just a little bit over half, would be female. So all the Associate in Arts majors, all the arts majors, a little bit over half of the people in the room are women. Part B is the opposite. Imagine all the women. So there's a room of nothing but women. And if they could all hold up signs for what their major is, about 16% of them would be holding up an Associate in Arts sign. So if we imagine a room filled with all the female students from that year, which is a huge number, 4,001 women. It'd have to be in the big theater at the college. But if you can imagine that big theater filled with women, nothing but women, nothing but the female students from that year. They're all wearing signs or wearing jackets for their major or something. 16.6% of them would be associate and arts majors. Now, this leads us to another definition because this will lead us to an alternative definition, if you will, of independent. Because if events are independent, if event E has no bearing on event F and vice versa, then the probability of E given F will be equal to the probability of E. In other words, F happening first has no bearing on whether E happens or not. By the same token, the probability of F given E is the probability of F. So let me see if I can say that one more time. So the way independence works is if the first event occurring doesn't affect the second. So having that first event is F, right? Given that F has happened. F already occurred, but that did not affect the probability of E at all. Probability of E is just probability of E. It's not probability of E and F divided by the probability of F and all that jazz. It's unnecessary if the events are independent. It's just going to be equal to the probability of E. Now let's see if that's the case here. So we want to see if the probability of AA and female are independent. Well, if that's going to be the case, then we would need the probability of AA and female, or AA given female, to be equal to the probability of female. Okay, let me write it out. I could have picked either one of these, by the way. I just picked the second one because it was convenient. So if they're independent, the probability of AA and female will be equal to the probability of female. All right, let me write that up. There, so we already found the probability of AA given female. It was up above. It was the bright pink one. So that was 0.166. And again, I did not have to choose this. I just picked one of them. And then, oh, I think I did this wrong. It's the probability of AA given female is the probability of AA, sorry. You take the probability of the second event, which is AA, associate in arts, and if it's independent, then the first event happening will have no bearing. So the probability of AA given female will be equal to the probability of AA, but the probability of AA, associate in arts, is 1194 divided by the total of 6548, and that's about 0.182. So, and these are not the same. Therefore, AA and female are not independent. If they were going to be independent, they would have to be the same. And again, there's nothing magical with choosing the pink one. I just chose the pink one. You could have done the same argument with the yellow one. 0.557 is not the same thing as the probability of female, which was 4,001 divided by 6548. So since they're not the same, that wouldn't have worked either. This leads us to a new rule, the general multiplication rule. So now that we have this conditional probability stuff in hand, that's going to lead us to a whole new way to do multiple probabilities, because everything up to this point was singles. You're pulling one single student, one single card, rolling, 2 dice, but rolling them once. What if you pulled 2 cards, 3 cards? What if you rolled the dice multiple times? Then that leads you to the general multiplication rule. So the probability that events E and F both occur is the probability of E and F, which is equal to the probability of E times the probability of F given E. Now remember, if they are independent, then the probability of F given E is equal to the probability of F, which means that this rule is equivalent to the one that you already learned in section 5.3. Namely, that the probability of E and F is the probability of E times the probability of F. So if they're independent, you can just take probability of F and stick it in there for that right-hand side. This part right here. You can just write probability of F if they're independent, which is the rule we learned in independence in section 5.3. All right, so now let's suppose we're going to take 2 cards in sequence from a standard deck without replacement. Now that's new. In 5.3 we kept replacing, but now we're going to do it without replacement. So we're going to imagine the probability of selecting 2 diamonds. So I want a diamond on the first and a diamond on the second. Let me write that up. Okay, so we want to know the probability of getting a diamond on the first card and a diamond on the second card. Well, that's equal to the probability of a diamond on the first card, so that's E, event E, times the probability of a diamond on the second card, given that we've already got a diamond on the first card, right there. Okay, so according to this, let's think about this. We should be able to find the probability of a diamond on the first card. That's pretty easy because there's 13 diamonds total in a deck. So that's done. So there's 13 out of 52 for that. Now we want the probability of we get a diamond on the second card, given that we already had a diamond on the first and it wasn't replaced. Well, since we already had dealt ourselves a diamond, there's only 51 cards left because we didn't put the card back. But because we gave ourselves a diamond on the first card, that card is sitting in our hand. So one of those 13 cards is gone. So that means there's 12 diamonds left for us to choose from. So the probability is 13 times 12 over 52 times 51. In other words, it's 156 over 2652. Which reduces down to 1 over 17, and at a decimal it's about 0.0588, if I did my math right. There we go. Okay, so now let's do the same thing here. We're going to describe in words and find the probability of QJ. All right, that's the probability of first drawing a queen, then drawing a jack randomly. So we want a queen on the first card and a jack on the second. But just like the last time, that's going to be the probability of getting that first card, so queen on the first, times the probability of getting that jack on the second, given that we've already got a queen on the first. Okay, well, there are 4 queens out of 52 cards. So the first probability is easy because it's the same thing you learned in 5.1. 4 queens out of 52, no trouble. But the second one, let's see here. Since we didn't replace the first card, that means that there's only 51 cards left. So now we have to ask ourselves how many jacks are left, given that I've already dealt myself a queen of some kind on the first card. Well, there are 4 jacks left because I didn't deal myself a jack, I dealt myself a queen. So there's 4 queens available for the first draw, then there are 4 jacks available for the second draw, but my denominator is changing because there's only 51 cards left. I've got a queen of some type sitting in my hand, then I can't get that card again. So there's only 51 cards left to choose from. So this is 16 out of 2652, which reduces to 4 out of 663 if you care. And that's about 0.06 in a decimal. 0.006, excuse me. All right. Let's apply the same logic to a contingency table problem now. Same problem we've seen before with our associative arts and female. So we want to find the probability that when we select one student in the fall, now this is just going to be a singleton, what's the probability that that student is both female and AA, using the multiplication rule now? Because we've already seen what this is. We've actually already learned it back before in section 5.1 or 5.2, but we're going to see it again now. So I want the probability of female and associative arts. Well, that's the probability of female times the probability of AA, given that you already know that first draw was a female. Okay, well, the female part, there are 4,001 females out of 6,548 in the group. So there's the chances that you're going to randomly draw a female. Now, given that you know it's a female, well, if I know it's a female, there's only 4,001 females. So my denominator has automatically shifted. I cut out the 2,500 guys in the group. Now, what's the chances of being AA and female? 665. So once I know I'm in the female group, then there's only 665 of them that are associated in arts. Now look what's going to happen here. 4001 and 4001 are both going to cancel away, or divide away, if you will, to 1. Right? So this and this disappear. And we end up with 665 over 6548, which is the same thing we already found in section 5.2. We already did this problem, right? But now I've proven to you that the general multiplication rule also will work to find that same answer, right? That you can use the general multiplication rule and say, I want this number 665 out of 4001 times 4001 divided by 6548. In other words, the chances of female was 4001 out of 6548. The chances, given that I know that it's a female, I'm in this row, and the chance of being AA in that group is 665 out of 4001. It's the same pink row that we saw earlier. Matter of fact, I can make it bright pink just to make it match. All right, I'll see you back here for more video lectures.